Today, we're going to be looking at the different types of chemical reactions. So we looked at a lot of chemical reactions in our last video when we looked at balancing equations. Sometimes some of the more students that are more observative can sometimes notice or sometimes ask the question of why do chemical reactions look different? So why is there sometimes two reactants on the left and only one product on the right? That's because there's different types of chemical reactions. So today, we're going to look at the different types of chemical reactions, and even more important, we're going to look at categorizing them. If you are able to categorize chemical reactions, you can actually predict what's going to happen when you mix two chemicals together. So by understanding types of chemical reactions, you can understand when I mix A and B together, I'm going to get this. So the different types of chemical reactions we're going to talk about, we're going to discuss 5 main types. We're going to talk about combustion, synthesis, decomposition, single displacement, and double displacement. Let's start the one that sometimes students can find confusing, but I really think is the easiest. This is an example of a combustion reaction. So combustion is when a substance burns in oxygen to provide an oxide. That sounds kind of confusing. So let's break this down using our general equation. Combustion is always going to be with a combination of oxygen. So you're always going to see oxygen being one of your reactants. In the combustion reactions we look at in grade 10 and even grade 11, what you're always combining oxygen with is a hydrocarbon. So what a hydrocarbon is any combination of hydrogen and carbon. This is actually a fuel. So you might have heard of propane gas before. Propane gas is a hydrocarbon. Gasoline is a hydrocarbon. So all different fuels that burn are different combinations of hydrogen and carbon together. So you're going to see some combination of hydrogen and carbon. As soon as you see oxygen, and as soon as you see a combination of hydrogen and carbon, you know this is an example of a combustion reaction. In grade 10, we only look at complete combustion. So in complete combustion, you're always going to have the exact same 3 products. You're going to have carbon dioxide, you're going to have water, and you're going to have energy. We just use E to represent energy. Energy is heat or light. So really, when you think about a combustion reaction, you should be thinking of fire because that's often what it is. So what makes combustion reactions easy? Because this doesn't look easy. What's easy about them to recognize is most of it, 3 out of 4 things, actually always stay the same. So oxygen is always here. Carbon dioxide is always here. Water is always here, energy is always here. The only thing that changes is the number of carbons and hydrogens that you have on this left-hand side here. So combustion reactions actually are easy in the sense that most of it stays the same. The products are always the same. The one reactant is always the same. The only thing that changes is your number of hydrogens and your number of carbons. So a little bit more about combustion reactions. Energy is produced usually in the form of heat or light. So when energy is produced during the reaction, we call it exothermic. So all this is saying is that since we're releasing energy, we're creating heat, we're creating light. This is an example of an exothermic reaction. We're going to look at these in a little bit more detail in grade 11 and grade 12 chemistry. And rather than just writing energy, we choose to just write an E. It's just easier. That's it for combustion reactions. So let's talk about synthesis reactions. Now, when I say synthesize, a lot of people think synthesis means create something new. One second. So when I say synthesis reactions, I mean we are creating something new. We're synthesizing something. So we're making a big something from 2 small somethings. So a synthesis reactions occurs when there's a combination of smaller atoms or molecules into larger atoms or molecules. Our general equation is this: A plus B equals AB. So something plus something is going to equal something combined. So you're going to have one atom. Let's say it's blue, and then your other atom might be red. And what's going to happen is atom A, which was by itself, and atom B, which was by itself, are going to come together, and they are going to form a molecule. So this can happen with individual elements forming molecules. You can also see smaller molecules coming together to form bigger molecules. So let's take a look at some examples of synthesis reactions. So how do I know this is a synthesis reaction? I had two small things coming together to form a big thing. Another way to tell this is a synthesis reaction is my plus sign is on the left-hand side. So I have a plus sign on the left-hand side. I'm adding things together, and I don't have a plus sign on the right-hand side. Synthesis reactions can also sometimes be called addition reactions. So this is an example of taking two individual elements, combining them together to form a molecule. Down here, we have another synthesis reaction. So we have carbon dioxide gas forming, combining with water to form carbonic acid. So here we do have our plus sign. So we have a molecule and a molecule coming together to form an even bigger molecule. So even though these aren't individual atoms, we still have two smaller things coming together to form a big thing. It's still considered to be a synthesis reaction. Let's take a look at our next type of reaction. This is a decomposition reaction. Decomposition, when you think about things decomposing, you might think about things breaking down, and that's exactly what a decomposition reaction is. So decomposition reactions occur when there's a splitting of large molecules into elements or smaller molecules. So we say our general reaction is AB will yield A plus B. Well, let's try to remind ourselves of what synthesis looked like again. Synthesis was A plus B yields AB. And now we're saying decomposition is AB yields A plus B. They're actually just the opposites of each other. So synthesis and decomposition is the opposite of each other. Synthesis, you're building a molecule up, and decomposition, you are breaking a molecule down. So in the next slide, we're going to take a look at some of our examples of decomposition, and you might see some of these might look familiar. So decomposition might be water breaking down into hydrogen gas and oxygen gas. This was the exact same example we had for our first synthesis reaction, just backwards. So decomposition is synthesis running in reverse. I'm breaking this molecule down into two smaller molecules. So instead of my plus sign being on my left-hand side, I now have my plus sign on my right-hand side. Same idea, this is our exact same reaction as before. So we've got our carbonic acid, and it's being broken down into carbon dioxide and into water. My plus sign is now on my right-hand side. So synthesis and decomposition are both simple reactions, and they are considered to be opposites of each other. Let's take a look at our next type of reaction, and this is our single displacement reaction. So when you hear single, you might think lone or by itself, and that's exactly what we're going to be looking at. We are going to be looking at lone elements. Displacement means to replace or to swap out. So we're going to be looking at reactions where one element is going to displace or replace another element. So let's take a look at our general reaction here. We have A, and we're adding BX. So here we have a single element by itself, and over here we have a compound. Now over here, again, we have a single element by itself, and again, over here we have a compound. So we can see that what's actually happening is B is forming a compound with X. A is a single element, and it's going to come in and it's going to take B's place. So A is actually going to displace or replace B. Now you've got B is all by itself, and A is now bonded to X. So notice that I have plus signs on the left and on the right. You know you have a single displacement reaction when you have a compound and an element on the left, and when you have a compound and an element on the right. So we're going to see a compound and an element on both sides. Notice that I've actually color-coded this as well too. What this stands for, blue stands for metals, and pink stands for nonmetals. So what's actually happening is we're having our metal come and swap out the other metal. You have to swap like for like. This could have been a nonmetal, so I'll show you what that would look like. Let's say that A is actually a nonmetal. And let's say that B is our metal in this case. So what would happen in this case? We're still going to have a single displacement reaction, but what you're going to see is just like up here, metals replace metals, non-metals are going to replace non-metals. So A in this case is actually going to swap with X. So you're going to see A, oh, nope. Forgot to change my color. You're going to see A is going to take X's place and be bound to B, and X is going to be by itself. The reason that we write out this formula here is because it's much more often to see metals swap with metals than to see non-metals swap with non-metals. So let's take a look at some of our examples. And let's see if we can figure this out. So single displacement reactions. So I'm going to help you underline a little bit. I'm going to help you color code. So we actually have a single element on this side, and we have a single element on this side, and we have a compound, and we have a compound. So what's happening is we've got our metal magnesium is going to swap and take place with our silver. So we've got our metal magnesium is swapping out with our silver. So now silver is by itself and magnesium is bound to nitrogen. Here, this is the other example I talked about. So here, bromine is actually a nonmetal. Since bromine is a nonmetal, it has to take the place of our other nonmetal. So our other nonmetal here is iodine. So bromine is going to swap with iodine. That means you're going to see iodine is going to be by itself, and bromine is now going to be bound to calcium. So that's our single displacement reaction. Again, we know it's a single displacement reaction because we do have our plus signs on both sides, but on both sides I have a single element and a compound. So that's how I identify my single displacement reactions. Our last, that's just my color coding. Excellent. So this is a little better than my underlining. Our last example is going to be our double displacement reaction. So just like a single displacement reaction was a single element replacing a compound, in this case, we're now going to have two compounds as our reactants, and that means we're also going to have two compounds as our products. So essentially what you're going to see is you're going to see like a partner swap. So you're going to see the two metals are going to swap, and they're going to be bound to two nonmetals. So let's focus on our metals here. Our metal here is A and B. So you've got A bound to our nonmetal X, and you've got B bound to our nonmetal Y. Essentially, all that's going to happen is A and B are going to swap positions. So what that means is B is now going to be bound to X, and A is now going to be bound to Y. So it's a switch. You're just switching the first elements. You can choose to switch the second elements if you want, just don't switch both. So you just want to make sure you just switch one of the pairs. So let's take a look at some of our examples. Here we have lead nitrate and potassium iodide. So here you're going to see lead and potassium are going to swap. So what that means is now you have potassium with a new partner, nitrate, and you have lead with its new partner, iodine. Here, same idea, sodium and magnesium are going to swap. So originally you had sodium bromide and magnesium iodide. Now you've got magnesium bromide and sodium iodide. So for double displacement reactions, you still have plus signs on both sides, but this time we have a compound, and a compound, and a compound. So that's how you would identify a double displacement reaction compared to a single displacement reaction. So I've got some practice questions. I want you to go ahead, try the practice questions, see if you can identify which type of reaction you have. So try to identify them, try them next, and then you're going to be asked these in your assignment. Once you've viewed this, next lesson is going to be called Putting It All Together, where we're going to take everything that we know about predicting reactions and types of reactions and everything we know about writing formulas, and we're going to see if we can get ourselves ready for grade 11 chemistry. So we'll see you in our next video when we take everything that we've learned and combine it together.